We're in section 4.3 on page 16. The example at the top says the graph of f prime of x is given. Find the critical values of f of x and determine if each is a local minimum, a local maximum, or neither. So remember, critical values are where the derivative is equal to 0. So the derivative is equal to 0 on my graph at our x-intercepts. So our critical values are at x equals, and we have -2, 1, and 3. And so if you want to think about this, you can look at the graph and kind of think about which ones are maximums and minimums. But remember, this is the derivative that we have. And so I'm going to go ahead and look at it the same way that we did with everything else. I'm going to make a number line. And I have my critical values at -2, 1, and at 3. And the graph is above the x-axis, so it was increasing to -2, then it's back above. And then at 1, it goes below the x-axis between 1 and 3. And then after 3, it's back above, and that's going to be increasing. So it says, let us know where there is a local min, a local max, and neither. And we have at 1, it goes from increasing to decreasing. So that's a local max at x equals 1. At 3, it goes from decreasing to increasing. So that's a local min is at x equals 3. And then neither is at x equals -2 because it goes from decreasing to decreasing. And that's not a local min or a local max. So the next part says, in summary, identify all critical values by finding the x-intercepts on the graph of the derivative. And then second thing says, if the graph of the derivative changes from positive to negative at c, so above the x-axis, then there is a local maximum at c. But we cannot actually find f of c. We're not there yet. That's more of the end of the semester or calculus 2. If the graph of the derivative changes from negative to positive at c, going from below to above the x-axis, then there is a local minimum at f of c. But again, we cannot find c. Next thing we have is the second derivative test. Let c be a critical value of f of x, and suppose the derivative, the second derivative, is continuous near c. Then if the second derivative is positive, then c, f of c, is a local min. So second derivative is positive, f of c is a local minimum. So that's saying that the second derivative is greater than 0 means that our function is concave up. So if it's concave up, then f of c is going to be a minimum, a local minimum. Likewise, if your second derivative is less than 0, which means it's concave down, we are going to have a local maximum at f of c. And if f, the second derivative of f evaluated at c, is equal to 0, then the test is inclusive. And we might be able to figure it out, but we're going to resort to using the first derivative test. So steps to use the second derivative test: to analyze critical values. Given f of x, first thing, find all critical values, finding where the derivative of x is 0 or undefined. 2, substituting in each critical value c into the second derivative to determine the sign. Again, if the second derivative is greater than 0, we have a local min. If the second derivative is less than 0, we have a local max. Circle the next example. We will come back to that.